When CO2 is released to the atmosphere, it contributes to global warming. We are developing a process to use CO2 instead as a carbon resource to enable carbon recycling. This is our bench-scale plant to develop this process. We are convinced that this technology will be indispensable for the realization of a carbon-neutral society.
The Japanese government has declared its aims to achieve carbon neutrality net zero greenhouse gas emissions by 2050. It will develop and promote the adoption of technologies for reducing the amount of CO2 in the atmosphere, including renewable energy and energy-saving technologies. However, eliminating CO2 emissions is challenging in many fields, and unless something changes, achieving carbon neutrality by 2050 will be impossible. It is necessary to reduce CO2 emissions as much as possible, while introducing technologies that capture and remove the CO2 released into the atmosphere. Producing syngas from CO2 and ammonia. Our society relies on numerous chemical products. Carbon is a crucial component of these products. At present, fossil resources like petroleum and coal serve as sources of carbon. Chemical products are eventually burned, releasing CO2. However, if this CO2 could be used as a carbon source, releasing new CO2 into the atmosphere could be avoided. The aim is to transition from a society that relies on fossil resources to a sound, material cycle society. Instead of extracting carbon from fossil resources below ground, carbon will be retrieved from resources already used above ground or from CO2 emitted through industrial activities.
We focus on the production of syngas. Syngas is a gas composed of carbon monoxide and hydrogen and is used as a raw material for chemical products. If we can make syngas from CO2, it will be possible to produce chemical products without using fossil resources. In fact, processes to produce syngas from CO2 and hydrogen already exist. Our newly developed process produces syngas from CO2 and ammonia. Why use ammonia instead of hydrogen? Well, because it is easier and more economical to transport and store ammonia than, for example, gaseous hydrogen at very high pressure or hydrogen liquefied at very low temperatures. Of course, hydrogen could first be produced from ammonia and then syngas could be produced from the hydrogen and CO2. However, we are developing a process that can utilize ammonia directly at lower temperatures, more efficiently, and at lower cost.
Let us now examine this method in greater detail.
This is our bench-scale plant. This is the reactor to which CO2 and steam are fed. And this is the reactor to which ammonia is fed. Metal oxide, as a redox medium, circulates between those two reactors to produce syngas.
In the reactor where the ammonia is introduced, a catalyst decomposes the ammonia into nitrogen and hydrogen. Hydrogen reacts with metal oxide to form water and metal. The nitrogen and water are recovered, and the metal is transferred to the next reactor. CO2 and water are introduced into the next reactor. The CO2 reacts with metal to form carbon monoxide and metal oxide, while the water reacts with metal to generate hydrogen and metal oxide. Carbon monoxide and hydrogen are extracted as syngas. The metal oxide is then transferred to the first reactor, where the same process is repeated.
This process has three major advantages. First, it can be operated at lower temperatures than conventional processes. Second, the quality of the syngas is high. And third, nitrogen can be kept separate from the syngas without an extra separation process. To develop this process, it is very important to study the process engineering aspects as well as the material engineering aspects of the metal oxide redox material at the same time. In the future, clean ammonia produced from renewable energy will be imported in large quantities from overseas. This will be used to recycle CO2 recovered from factories, waste incineration plants, and other facilities. We believe that the new syngas production process we are developing will be an important technology for this purpose.
Utilizing minerals to sequester CO2. In addition to technologies to convert CO2 into resources, we are also working to develop technologies that use minerals to directly incorporate CO2 already in the atmosphere and prevent its further use. This mountain is comprised of olivine, a type of peridotite which makes up the Earth's upper mantle. The surface of rocks that are exposed above ground eventually bonds with CO2 dissolved in rainwater, transforming into carbonates. This natural process, however, takes an exceptionally long time. We are developing a technology that artificially accelerates this process to remove CO2 from the atmosphere. This is one method of carbon dioxide removal.
This is a small rock containing olivine, a mineral found in large quantities in peridotite. If this is left exposed to rain for a long time, it will eventually react with CO2 and turn into carbonates. However, this process takes a very long time, year or even decades, to fix a few kilograms of CO2 as carbonates. We would like to shorten that time to a few hours, preferably around an hour. This is an experimental setup to enhance the mineralization of CO2. Finally, crushed olivine particles, CO2 and water are mixed together and stirred at high temperature and pressure. Calcium and magnesium alkaline earth metals in the olivine bind with the CO2 to become carbonate. We are also investigating other minerals such as basalt in added to olivine for CO2 carbonation. Natural mineralization of CO2 takes years or even decades, but we can make it happen in just few hours with this approach. This may seem impossible, but we are taking on the challenge.
We approached the realization of carbon neutrality in 2050 from the perspective of the effective use of CO2. Novel processes and technologies need to be developed to convert CO2 into useful products. We will continue to work with universities and institutes around the world in our research and development efforts.
Please join us in realizing a carbon neutral society.